Welcome to another GC Basic tutorial. This is for the 16F175 chip family. This is part 12. So this is part 12. This is using graphical LCDs or GLCDs, graphical LCDs. This time we're going to be using I2C, and it's really a prerequisite to have done part 11 to ensure that you've got I2C communications, but it's quite interesting. So please like and subscribe. I'm in this for the like and subscribes. Just a few more and I will be very grateful. So part 12. We're going to be looking at using a graphical LCD, GLCD, using I2C, and then in the next video I'll do this very similar but using SPI, serial peripheral interface. It's slightly different. You might have a different requirement, but the videos I'm going to the demonstrations can be ported to SPI. I'm just showing the capabilities. So I'm assuming that you've got your GC Basic software installed and your IDE, your programmer is working. I've swapped programmers from the previous videos because I was doing other work, and I'll show you that. You've got the 175 chip family operational. You've got some LEDs, a potentiometer switch, USB TTL converter. Now we're not going to be using all those, but that's what I've got in this setup. And you've got a GLCD device I2C attached, and it worked in terms of discovery. It has shown up in the previous tutorial as the correct address. Now, spoke about this in the previous. I2C is a bidirectional communication protocol that uses an open connector or open drain, so the line's actually floating, and we're going to the integration inside the microcontroller looks for pulled up resistors, so the lines go high. And why that happens, why that's important is because if the lines float high or get pulled high by resistors, it means that you can have more than one device on the bus on these two lines called the serial data line, SDA, or the serial clock line. And because these pull-up resistors exist, the clock can be controlled. The communication can be controlled. It's a very simple protocol. Typically, voltages of 5 or 3.3 volts, but other voltages are permitted. And be careful, just always check your voltages with these types of devices. I'm using a 5 volt device. A lot of devices are 3.3. Beware of voltages. What am I actually got hooked up here? I've actually got hooked up the SDA and the clock line. Look, I really should do that again, shouldn't I? Yeah, that was not. It's on port C. It's on these pins here. Port C4 for the clock, port C.5 for the data line. SDA, SCL, they're used interchangeably. This is where they're actually attached on the chip. These ports 16 and 15 and 16. Okay, last time I'll be showing this. So I have got some pull-up resistors on the VCC. That's important. These are my pull-up resistors, one here and one here. Typically I use 4.2 or 2.2. And I've got those lines pulled north. And then I've got a yellow cable connected and a blue cable connected to my GLCD device. I use those colors always because it's just so clear when you have multiple I2C devices. You can go that's the clock line, that's the data line. One is blue, one is yellow. There's no confusion. Spoke about this, and we're going to see this protocol of I2C start, an address, sending data, and a stop, all happening in the background because it's within the library. So we've seen this, how this worked in discovery. We sent out a start, we sent out an address, and if it responded with some data, then we knew it was there. But this time we're going to send real data out. Don't really need to peel that slide back. But what is important is that we're going to look at peeling back the libraries and the architecture of GC Basic. So I'm going to turn my pen on. We're going to look at a user program. It sits here. And in the user program, you write your code. And it has, you could add in your own user functions or things called converters or external sources. There's lots of stuff you can do, but we're just going to look at a set of demonstration GLCD devices. Well, they call the GLC libraries. Oh, and there's libraries. There's 100 and, I'm so sorry, 125 different libraries. Look, oh, so sorry. Oh, 125 different libraries. And a library, you include it. You use the hash include, and it pulls it in. And we're going to see a number of libraries being used in these demonstrations. Certainly ones are GLCDs and the maths. We're going to see them in use. Once you've included them, then you extend the capabilities of the language and therefore your program. Now these libraries may call different low-level libraries, and those low-level libraries will refer to, and we've seen one of them, USR, the serial. We're going to see I2C, we're going to see SPI, but they will be defined, and the calls into these will be defined in the user library. Now you can call them directly, there is nothing to stop you from calling them directly, but generally a library is a more robust way, is reusable. And from this complexity, even if you change the chip at the top, the libraries and the low level all changes, you generate a hex file down here for your specific chip. So you can, by using a library and these low level functions, you can change your chip at the top and your program should still work. It should still generate a hex file. So we're going to see GLCD in use and how that calls different libraries. So what we're going to do is we're going to just review to make sure we understand that we've actually got the I2C port set up. Bring my pen up here. We're going to do that. We're just going to review that. And we're going to use the USR. Do we actually use the USR? I think we're going to set it up. And then we're going to configure the IC or set up the I2C. And then we're going to look at some demonstrations. 4 of them. There's what I call primitives. There's a BMP converter, some Sprite, and a Voltmeter. So what I'm going to do is rip through these at speed, okay? All right. My setup today is this. I have my GC basic board, and look, it doesn't here. This is the yellow one. It looks white on the video. And this is blue, and guess what's coming down here? The clock is coming down the yellow, and the data's coming down the blue. I know that because I always use those colours. So what I'm going to do, I'm going to zoom in on that video. Look, there's a GLCD. It's operating. Now, if I manage to do this properly, yeah, I'm going to get that into focus for us first, okay? Because that is quite annoying. And what I'm having to do in here, just so I'll do it so you can see it. A bit disappointing. I have to do it like this, look. I have to configure the video and change the zoom rate so we can actually sort of see it live. Oh, that's not working, is it? How am I going to do this, eh? Let me just turn off the automatic. I'm just going to try and get it manually into focus. Click, click. No, that hasn't worked. Let me zoom in on the hand controller. I'll default it. Brilliant, eh? Who's used cap? Oh, it's in focus, look. Now I can zoom in. That's really good. Okay, I'm just going to move my camera back. There you go. We're going to see that operating. Sorry about the interface, the interlace. That's not something I can control. Okay, let's go straight into my desktop. And I'm going to press the Windows key, bring up GC Studio, GCS. That will take me into the GC Studio entrance. We've seen this before, and I'm going to take my chip range demonstrations. Close that down, because that's what I had in there previously. Won't save that file. And into my desktop. This is the IDE. I am going to open up the Explorer. And there's a whole series of demonstrations. I'm going to take you straight into 190, which is using a specific GLCD, an SSD 1306. GC Basic supports so many different GLCDs, and we're adding another one tomorrow. We're always adding them. So we're just going to, this particular device that we were looking at, so we'll look at that device in the cam. This device is an SSD 1306. They're dirt cheap. And there's a particular driver for that, and that's what we're going to look at. Shut down the Explorer, and then we'll go into the code. So let's go straight into the code. The green code is commentary. You can read it in your leisure. So we're specifying this specific chip, and then option explicit. This is the PPS. We've seen PPS work. Essentially, what you do is you go into the PPS and function key F4, PPS tool. It will then open up the PPS tool, and then we select which ports we want to use. I'm using, and here's my chip selected. I'll zoom in for you. I'll bring that into focus. There we go. I'm using, as I said, SCL. I'm using the SCL on C4, looking at my diagram, and I add that in. The SDA one, that's on, I believe, C5. I add that in. Now I've got my code. You can add in the serial if you wish as well, but we don't need the serial. But that is how you add it. Copy that and paste that into your code. There we go. Paste it in. The constants are exactly the same as previous, apart from we've seen this in the previous demonstration about setting up the I2C interface. So we're going to set the baud rate for this to 400. The hardware, or the I2C baud rate, 400. It could be 100, but this is a 400 baud rate device, and that will be on the specification on the data sheet. Two constants needed just to tell it which ports the data and clocks attached to, C5 and C4, and we set the ports to inputs because these particular ones are inputs. That's because the lines are floating. Then we're going to set up the GLCD. Now, the GLCD, this is the call in the library, hash include less than glcd.h greater than. This line here includes the library. Then you define your type, GLCD type as a constant, and we've said GLCD type and SSD 1306. And the address, I2C address, GLCD I2C address 78. Well, we know that from the previous, but also I know that because it's written on it. If I show you my desk cam, look, it's actually, why is that the board's rotated for some reason? It says here on it, look, 78, hex 78. Then you can actually set up this particular constant, which is GLCD overrun protect, protect overrun. That is, if it draws something off the outside the display, it doesn't draw it. It doesn't bleed over, and so you can protect the bleed over. Now the rest of this is going to use commands and variables to put things on the screen. So let's get that done. Let's do it. I pressed function key F5 to program it, and it's now programming my PIC16F175xx. I have a PIC16F175xx attached today. It was happened to be attached. Now what it's going to do now, it's going to put some text on there. And we can see on the left-hand side on our code here, it's going to print GC Basic, Anobium, a portability demonstration, the chip name. These are, so we've changed from hardware serial, which is the USART, to GLCD print. And there's a whole series of commands that start with GLCD print. And there we go, look, it's just printed exactly what I said it would. And now it's drawing circles, lines, boxes, filled circles on the screen. It's printing. If you look at it, it's printing long numbers in hexadecimal, words, bytes, strings. Let me see if I can get in any closer to that. Ooh, ooh. That's as far as my zoom will go, but so I can certainly do it like this. Look, look at that. I'll try and get that back in focus for us. Testcam of properties. You can see over here. I'm trying to configure that for us so that is better. Oh, that's better. Look, there we go. I'll okay that. So we can see that we've got special characters, letters, etc. And we've got some of the parameters. 32 megahertz is coming through from the microcontroller. So if I reprogram that, what else can I do? Well, if you look at that, was demonstration 192, so it really is a good demonstration, shows you the full breadth of capabilities. Most of the commands start with GLCD, print, etc. Now, what you're seeing is what's called interlace. So this tearing that you're seeing on the screen isn't actually visible to the eye, it's just visible to the camera. Let's look at 220, 200. Well, whilst I'm in here, I'm just going to Control F, GCB, and apply that filter so I don't see all the other temporary files. Right, 220. If you want to draw a BMP, here's a method for drawing a BMP. And so what this is going to do is going to take the BMP file, which is external to the compiler. It's going to transform that, and it's going to put it on the screen for us. How do we do that? I'm not going to show you the full setup of the header is all the same. The setup of it is identical. About to load a bit. It's done it. How does it do that? Let's look at the code. Include. And I've included a BMP, an Obion full BMP. Interesting. And here's the routine to make that happen. It actually creates a table. Reads the table in, and puts it on the screen for you. And you can do that by going read table. I've got a table called an Obion full. And by the way, the table is created dynamically. It's not in the program at all. It's external using something called a converter. Then I do some maths, and eventually I put it on the screen using the GC Basic instruction called pset, which is pixel set, and it puts it at a particular location in the x-axis and a particular one in the y-axis plus a little increment. If I just turn off the camera, which is that's the increment current char, and then it's either the background or foreground, and it iterates through a very long table. Now that's the end of the program. There isn't any more to the program. It essentially reads the table in and says put it on. So where did that table come from? It came from a converter, and that converter is equivalent to the name of this, a Nobium BMP. If we look in here, a Nobium 4 that's been created, and here is a table of numbers, huge set of numbers, but you don't have to worry about it because the converter does it all for you. And it says in here, it found a valid BMP, got some metrics, got a size, and it says the BMP width is 128 pixels by 64, and it puts it on the screen for you. So you can pull in BMPs. Let's look at some performance. Same header. This code was written by Stan? I think it was written by Stan, one of our developers. And this one here sets up the GLCD in exactly the same manner. And then it's going to put some sprites on there. And this demonstrates how you can use sprites. And essentially all it's going to do is update the pixels. And it draws a sprite in a function that Stan has written. If we look for that, is it a function or subroutine? It's a subroutine. And it says here, draw a sprite at a particular XY location. And then he uses the pset command to actually if you walk through this, it comes down and draws the pixel in the correct position. Let's have a look what it's actually doing. I think that's where the value comes. Believe it or not, that's a smiley face bouncing away. So you can write a game, and there are people who've written games based on this exact routine. And all this routine is doing is using the derivatives or the base GLCD commands to draw pixels on that screen. Stan defined in his program here his icons. And if you look at this red table data here, you can essentially work out that the shape of what's on the screen by looking at the raw data in your mind's eye. So Stan has provided that to us as a demonstration of the capabilities, and in here you will see it reads the table, does some rotation, and puts it out on the screen. Now, this is using very little RAM, very little RAM. And if I just compile the program, we'll see how much RAM this is using. This is using 1,125 bytes of RAM. However, 1,028 of that, 1,024, sorry, is the buffer to the display. It's not using very much. It's using very little. It's very clever. It's a very clever program and a real demonstration of how you can actually optimize code using GC Basic. Demonstration 220. This is a voltmeter. Now this one includes trigonometry. Trig to two places .h means it's going to pull in the trigonometry. The setup of this GLCD is exactly the same as previous, all the same constants, and then there's the main program. And essentially what he's going to do, he's going to draw, take in the value of the ADC, I will program it, take in the value of the ADC, and then display that as a voltmeter. And that's what we saw when we first did it. And here it is, read the AD. We've seen that in very early demonstrations. Scale that number. This scale is the same as the input as the output. So 0 to 255, it's 0 to 25. It allows you to calibrate. Then it does some string handling, does some clever stuff, but then it's going to do some drawing using maths. And I'll come on to that once we've seen it all working. It does a line, prints out the voltage, draws a line and waits 20 milliseconds. It's a very basic voltmeter. If I rotate the potentiometer, 0, rotating the potentiometer to 5. That's my operating voltage. Obviously, you'd have to recalibrate it for different voltages, but it's showing that you can do some clever stuff. Now, so where did it get, why is the trigonometry in there? The trigonometry is in there to work out this line, to ensure that this line is in its right position. He's done that by including the library, and then including that library exposes that function. If I look in the code, here it is, the sine and cosine. I'll shut down the sine and cosine. So if I take that library out, those won't be there. So let me just find that line. Trigonometry, I'm going to comment it out by pressing Control / comments it out. I will try to compile it. And it says, old angle, sine angle, these things are not explicitly declared. That's because we're calling functions and capabilities that are not actually available. And if we look in the terminal window, this is the problems window. If we look in the terminal window, you'll get a bigger list. Look, it says here, variable sine not explicitly declared. So let's have a look at that. And it's because sine doesn't exist. Cosine is not publicly available. We haven't included it. If I revert that and put it back, I'll just compile it. We know that's going to work. and it's successfully compiled it in less than 0.1 of a second. So what we've got is a terrific little voltmeter that we can play with. Yeah, all this is over I2C. All this is via the libraries and the low-level libraries that we saw in the diagram. And so we're seeing a user program exposed capabilities, GLCD, trigonometry, etc., etc. And then the low-level communication protocol of I2C is abstracted from you. You don't need to do the start, send the data, send. You can if you want to. You can write your own libraries and write your own functions, but these are ways of making it easier. With that, back to my PowerPoint. Get rid of that. It's gone. So, next video we're going to look at is a SPI, very similar, using GLCD. It's a different library just to show that how to configure SPI. Good demonstration because you get GLCD devices, RAM devices, etc., and they all use SPI. With that, enjoy.